easy signal goes. I will have two case studies, what we did with the standard data and talk about the publications what we did. Part 2 will be on live data acquisition system, which is a portable battery operated device. We will acquire it and we will also see what all options available in the particular setup that we have used it. Okay. So, let me start this. We took a database from the Purdue University US for the mental alertness and computations. So, we had two set of data, rather the analysis that we focused on. One is the letter composing and another one is the figure rotation. So, as and when you are thinking like composing a text, they have acquired the data, it is a standard database available, and also as and when the visual thing is rotated, the figure rotation, again the data is acquired. Using this data set, our interest as an organization was to control something in the real time. It could be an arm or it could be a robocar, to showcase the POC, proof of concept. Though we are into research, but we are end application is what matters us rather than the pure research, because we are into the other space of academia also. So, I have a small video on how we were able to do that for the letter composing and the figure rotation. This is one case studies I will discuss. The second case study is from the deep database. I am sure whoever is into easy analysis, you are aware about the deep database. So, I will take that as a case, what we have done and what is the publication that we are planning it on this. Part 2, as I said, we will move on to the real time data acquisition and I will spend more time. You can also see the devices from a very close angle, you can acquire it yourself, how easy it is, and that way we can plan it. So, the process which we followed for the Purdue data set was, we went with the wavelet based feature extraction and we tried out with the ANFIS classifier to give a very good learning rate. So, we were able to achieve, the error was, the comparison is here. This paper is freely available, I can also share this. So, it is tabulated here. So, the error was reduced drastically with the ANFIS. So, there is no data acquisition involved here, took the easy data, pre-processing is the next step, where you typically end up doing a low pass filtering to eliminate the high frequency components present in it. Then you go with the feature extraction and we selected wavelet based feature extraction. Wavelet is a transform which will give you the time frequency resolution of the data. Then these decomposed coefficients or the wavelet coefficients were given to the ANFIS for the training as well as for the testing. The objective was to control the device. Okay. I will just so accept acquisition in real time. So, what all the pre-processing we used in this work? As you can see here, the normalization is done as a first step. The signal was filtered between 0.5 hertz to 40 hertz to eliminate the 50 hertz interference also. And from this data set, we are particularly interested in a delta which will be dominating when you are doing letter composing or mathematical computational case. So, we focused on delta, theta, alpha and beta. So, from the feature extraction per se, so we used a wavelet to decompose it. So, you have a low pass filter, high pass filtering which goes in the wavelet decomposition, which is a filter bank theory. So, we went with 3 levels of decomposition and we used Debasys-14 wavelet. Dr. Ingrid Debasys she is a mathematician who worked on wavelet, and in her name there are hundreds of wavelets. The next one was the ANFIS classification. So, it is a neurofuzzy, both rule driven as well as self learning. So, it makes both neural network as well as the fuzzy logic. Other than this, you have couple of other classifiers which are widely used in the easy signal processing, namely the SVM and the k-means. We will also see one case where we used SVM as well as k-means. So, this is driven on two sets. One is there is a self learning process in it, and there is a rule based process which will follow this. So, we formed two classes of data. The first one is of letter composing, the second class is of the figure rotation. So, once you have extracted the features using the wavelet, then comes the training process which we saw in the previous one. The next one is the testing. So, we used 0 and 1 for the activation. We assigned 0 for the letter composition and 1 for the figure rotation. Based on this 0s and 1, we had a microcontroller, namely the Arduino. The 0s and 1 were given to the Arduino, and from the Arduino we were able to drive the external device, right. Right. So, for the letter composing, to control the device, if it is 0, no action, if it is 1, we used LED to on. So, this is a setup. This is the setup in the neural network training as well as testing. So, people who are working on the analysis tools, to name Scilab or commercial tools like MATLAB. So, you will be aware about how to train the data. I will not get into that, and how to test it. So, there were two process here, one is the training and another one is the testing. Just mute the audio and then run it. So, we were able to interface the testing, the generation of zeros and 1 from the computation, and once zeros and 1s were generated through the Arduino, you are able to drive the external devices. So, you have a task to select there in the training. So in the testing you have multiple options, letter composition or figure rotation and so on. Now you have set particularly the figure rotation. So as and when the zeros and ones based on your analysis goes, so you are able to either move the robocar in the forward direction or in the reverse direction, right. So for task 1 it was forward direction, for task 2 it will be a reverse direction. So this was a proof of concept to showcase the capabilities on this. The second one is with the deep data, what we worked. So by this time you have already started with the how the brain works, how the EEG signals, the different frequency components, the different signals which are part of your EEG, you are aware by this time. So in this we focused again on emotion detection, and it's a huge data. Deep is a very big database. I'll go directly there. And the applications of emotion detections are plenty. One is in rehabilitation. If we are able to understand the emotions of the other side, it can help in the rehabilitation. You can enhance the companion realism. It will also help in the counseling to if we are able to understand the other side's emotion. So as a counselor it will help you to counsel them better. Of course the healthcare, which is a theme of this workshop, in terms of treatment also. Autism is another disorder and the number is more in India, so EEG is playing a very vital role in understanding their behavior and emotions and then trying to respond to them. Music therapy is another one, probably the other resources might be talking about that. Alzheimer, how to have the positive effects of on that. Of course e-learning. So there is an area which is called the neuromarketing. So based on the behavior of the customer, we need to decide what to sell. So that's another area from the commercial perspective, and a lot of research is also happening in the neuromarketing. So tutoring also. So basically wherever we need to understand the emotions of the people with whom we are interacting, so the interaction becomes very, very fruitful and we can able to handle their questions. We are able to help them with whatever they will be requiring it once we understand the emotion. So EEG plays a very vital role in understanding the emotions. So the EEG signal processing, making an intelligent system using your neural network or fuzzy logic to control the devices which has got applications in the assistive technology domain of biomedical engineering. Those are the applications of it. Okay. So in this case study, what we did was the data acquisition and then the pre-processing. So in the pre-processing we went with the principal component analysis, PCA, the covariance, and then the common average referencing method. In the feature extraction we went with the basic features of the signal, the Fourier transform, PSD, power spectral density, and we also used the discrete wavelet transform, DWT's coefficients for the feature extraction. Then we tried out with two classifiers, one is a SVM and then the k-means, and we were able to classify the status as a sad or a happy. Okay. So I'll also run a case study to show that. We will see this data acquisition in the real time shortly. As soon as this presentation is over, we will see that. So, you band limited the signal between 1 to 50 hertz. In the previous case, it was from 0.5 hertz to 40 hertz. You can eliminate the power line interference by going with a notch filter design. The typical 1 to 50 hertz can be segregated into alpha, beta, gamma, as you already come across. So, in the pre-processing, we tried out with this common averaging method and we were able to get a very good results. I will be showing the results shortly. The another one, we went again with the basic feature based on the principal component analysis, PCA, and independent component analysis, ICA, is also preferred in the EEG signal analysis. You will find a lot of research happening on ICA, but we tried to get better results with the PCA. So, this is the time domain signal and you can see the corresponding frequency domain signal. This is for the researchers. We just tabulated by doing a literature survey. What are the typical features that are preferred in the EEG signal analysis? So, if you see the features, leaving this aside, if you see the list of features that are preferred in the EEG signal analysis, especially for emotion detection. So, you will find energy as one of the feature. You will find wavelet coefficients. You will find out the power spectral density computation using Welch method, a simple frequency FFT. You will also find some papers you going with a CSP, common spatial patterns. Then higher order crossing, that is the high frequency component. The AR, autoregression, Euler-Walker methods for estimation of the autoregression model. You will also find people trying out with STFT, short term Fourier transform, also 512 point STFT, but that has already overcome using the wavelet. So, we just try to give the list of features that you will find across in the literature survey. So, broadly for the emotion detections, what we found out is these are the features which are required to extract from the data for training the classifier. So, the Fourier transform, the power spectral density, the DWT coefficients. So, I will not get into the fundamentals of frequency, PSD, FFT. I assume that you are aware about it. So, typically this classifier gets these features and then there is a training process and then there is a testing process also. So, the types of classifiers which we tried out falls under these three. One is a supervised, unsupervised, and then reinforced. We tried out with the SVM, support vector machines, as one of the classifier, and from our literature survey so far, SVM has given us better results in terms of the classifier, because as a researchers these are the few questions that we will have always to begin with. What kind of features to select, how to identify a feature, what could be the best classifier for emotion detection if that is the research area. So, when we do a literature survey, probably SVM is what we found out, and we also experienced it by using SVM, and whatever set of features we had selected from there, we picked up few features and then we were able to get good results in terms of learning. So, SVM is based on this linearly separable data concept, which is the best to separate. That is the SVM. I do not think I will be able to run this video. So, I will go back to the first one. So, this we published it in Journal of Medical and Engineering, though we are not a research organization, but we have a research flair being in the commercial space also, so that we keep on interacting, and out of interest we will be doing these kind of a case studies. So, the error, as you see, using the ANFES, we were able to reduce it drastically after 500 iterations. This is the one case for the offline with the Purdue data, and another one is with the deep database. Okay, I'll skip this video. Just discuss the results. So, there are 40 peoples, 32 different trials available. So, we went with these parameters, these features, and when we clubbed different features, you can see the efficiency of the classifier. It is almost 96-97% with correlation and power spectral density. With wavelet energy alone, we were able to achieve 93% of the efficiency, and so on. So, we tried out different features combinations. We gave a single feature to a classifier to see what is the efficiency of the classifier learning process. So, this is another observation from the deep data. Since there are different subjects, and even if you show the same video or picture or audio stimuli, the emotions are different. So, standardizing that is also a challenge, right. So, this is also another observation which we made from this database. Okay. So, once we selected the PSD and we went on with subjects, different subjects also. So, subject wise we try to analyze what feature can be used to what kind of people. So, to that extent we can able to get insight into the data. So, these are the combination of PSD ratio, it is a comparison what you can see here, different learning here. So, these are the two offline cases which we tried out. Let me go ahead with the real time data acquisition and what all we can do with the data, and how all we can take this data outside this data acquisition environment, and how do we use the algorithms that you would have written in the signal processing to apply it onto this data. So, I have a 8 channel data acquisition system. Okay. So, this will be communicating to the data acquisition software or the system through the Bluetooth. Okay. I will just turn on the Bluetooth. Now, the Bluetooth is off here. I will just turn it on. That will also tell you what is the battery in terms of percentage left out in this. So, this has got 81% of the battery now, and the Bluetooth is connected. Okay. So, this any data acquisition systems in the EEG also comes with the cap with which has got 10-20 electrode systems, right. So, from the nozzle, so 10%, every 10-20% you have the points which you would already come across, and we have a reference as a CMS and DRL which can be plugged into your earlobe. The positions depends on what kind of experiment you wanted to do, what kind of data you wanted to get out of it. For all emotion related applications, emotion detection, drowsiness detection, those kind of things, we predominantly depend on the frontal electrodes, and you will see most of the electrodes are in the frontal lobe. So, you will not find any electrode in the occipital region backside, that is not the objective here. So, this software has different options, as you can see from here. The first one is in the time domain, you can see all the data, you can see the raw data, you can see the visualized filtered output also. You can also see the placements. Now, wherever we have connected these electrodes, you can able to see it, and in the A channel you have an option to configure this. So, you can say channel number 1. So, this is the channel number 1, channel number 1 has gone to F7, right. So, channel 1 goes to the F7, which you can configure it. Okay. So, like this you can configure channel 2, 3, 4 and so on. You will also get to know what all channels are connected, which is indicated here. This setting you can do it. You can save the data in multiple formats. There is a format called as a .ez, which can be read in most of the data analysis tools. You can read it in MATLAB, you can read it in Scilab, you can read it in Python. It will be ASCII file format. You can write it in this file. The output directories and you can set it. So, this is the basic set that you need to do it in the beginning. Before that, if you have multiple devices, so each device is unique, which each device has a MAC address. So, you can pair it with that. So, you can scan so that any other devices which are around this will be showing it here, and out of that you can pick up any one device. So, this is the one time setting. Then in the analysis part, you can see the spectrum per channel in the real time. You can opt for F7, F3, whatever channels you wanted to see the. You have an option to see the spectrogram. You can see the delta, theta, beta, gamma. Individually also you can see any frequency component that is of interest to you. So, this skull will basically give you the field distribution around each channel. Okay. So, you can go with the FFT or you can go with the power spectral density. Okay. So, this is the setting part before beginning the experimentation, and of course, you need to have a protocol to conduct the experimentation. So, whether you wanted to acquire the data for 2 minutes, 3 minutes, 5 minutes, and how do you wanted to trigger the emotions, that is also you need to define it in the protocol. So, let me connect this device. Okay. So, we have seen where the data is connected. I need your help, anyone's help to connect this. Yeah. This should go to the earlobe. can increase the scale, you can decrease the scale. So, you can keep watching FP1 and FP2. You can see the blink 1, 2, 3, 4. Let me close my eyes and you can observe the data. Did you see the change, right? So, you can have a blink which is the EOZ, which can be observed in your FP1 and FP2. I will blink in sequence. So, you can use any of the channels for the averaging. Okay. Any one channel you can keep as a reference. So, you can see the connectivity. We are only viewing the data here, we are not yet started recording it. So, you can do this to allow me to settle down as a subject, so that whatever protocol you have defined, whatever emotions you are trying to induce, so I will be responding to you, according to your protocol, right. So, we normally allow the subject to settle down for 2-3 minutes time, and once the subject has settled down, then you can start recording the data. Okay. So, let me start recording this data. So, it has written the data to the path wherever you had mentioned it. So, you can basically set what is the time that you wanted to do the experimentation and so on. These are the dry electrodes, what you can see here. So basically it will be on your skull, so it's a non-invasive electrode, what you can see, and you have a wet electrode also. I'll show it at a closer interaction. So basically I'll just turn it off. So I would like to give a feel of what would be the advantages of portable devices. You would have seen long hanging cables in the hospitals for the data acquisitions. So you can try out for 2-3 minutes on your own. You can start the experimentation on your own. Now you have seen the options available. The configuration, this is one time, so I have already done it. So once you decide what are the channels you wanted to connect, you just have to change this depending on the channel of interest to you. Once you set this, then it's a data acquisition. You can start the acquisition on your own, and whatever analysis that is provided here, you can use that basic analysis in this. And since the raw data is with you in the .eg form or EDF form, that can be taken across for the analysis environments. Any tool you can use it to do the processing. Right? It could be open source technologies, it could be commercial available tools to do the analysis, and from the analysis you can derive the zeros and 1 if at all your interest is to control the hardwares. Right? So anyone who wants to try out, you can start on your own. Yeah, you have accelerometer here, XYZ. I will leave the system. I wanted to give a feel of how easy or how he can start on his own. So I'll be, yeah, you can come. I'll be just watching it. Only thing that I will help him is I'll just plug this reference electrode. Okay. You can sit closer, comfortably. Yeah, relax. In this, yeah, position wise it is 39 actually, but in this, yeah, any of this.
And from that drop down menu on that software you have to select
channel configuration. You are right. Comfortable. I'll turn it on. So I just turned it on and then wait. Yeah, now it has system has recognized that it is on now. So signal monitoring is still off. So you can start the signal monitoring. You can settle down. You can sit.
So sometimes the color decides that electrode numbers
Oh yeah.
are coming red and green.
Correct. That we have given indication to see whether what is the drops in the packets. The data from here to here, there will be a loss because it is transmitted through the Bluetooth.
So there are loss sometimes.
Yes. So that is where it needs a training. The subject has to be trained to give you the data.
What's the sampling rate?
512 hertz in this.
So only once you stop the recording process, then only you can import the data.
Only once you start acquiring, yes, it will. Now, as of now, it's only monitoring now. So you are only able to see the data coming onto the screen. Nothing is getting recorded, right? So once you say recording start, then it will start recording it.
I'm asking
Yes.
Only after you stop the recording, then only you can import or export
Yes.
the
Yes.
data file.
Yes. Yes. Yes.
Not in between, like no buffering is done.
No. 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 It will write it into the file, right? That file can be read in the real time. So you can blink in between. Can rotate your head. So you have an accelerometer also there. It can be seen from the bottom there. X, Y, Z. So there are different types of cap size which comes. Now you can see everything is green here, so all the electrodes are connected firmly. Right? Yeah. One second. Thank you. Any other questions? नहीं नहीं. Right. Right. So the objective was two in the beginning. One is whatever we have done as a organization as far as the easy data acquisition is considered. Our interest lies in developing the hardwares. Our interest lies in developing the algorithms to enable the researchers. So we were researchers and we are researchers, though into the other activities. So we keep working on different types of hardwares, especially the portable hardwares. One limitation that you see in terms of these kind of devices is the communication that it has. So it has got a Bluetooth communications, and as we understand, if we move beyond 2 meters or 3 meters, probably the communication stops. You will not be able to receive the data. So that is where the RF based or a long range data transmission becomes the necessity. So we have a prototype where we are able to transmit up to 20 kilometers. We have a long range chips these days in the market. You have chips from different makers. I will not name them, but there are long range chips are available, and we have done the prototype. We have tested it up to 20 kilometers. You can transmit the data at the rate of 40 Mbps. So literally you can transmit the data, the audio and the videos, right. So they have been used in different applications. So medical, we are trying to evolve it. So they have been using in the security, where you wanted to transmit the data from the border to a remote 20 kilometers or 40 kilometers radar, and you can always go with a hoppers. So every 40 kilometers you can have a hopper, it can transmit another 20 or 40 kilometers. So that is the kind of technology as far as the transmission goes. Probably most of the devices, whatever we have seen in the easy data acquisition systems. So they mandates you to sit very near to the system because they're all Bluetooth enabled. Most of them are Bluetooth enabled. I'm not talking particular to this device, but most of them are Bluetooth enabled, and hence it necessitates you to sit very close to the system. So system based solutions you can develop it. I wanted to control, from the monitor, from the system, or increase the concentration. Those kind of things are possible with these kind of portable devices, but if at all it involves controlling other devices remotely, probably this has got a limitations. So another requirement, as was asked rightly, is the sampling rate, right? So as you understand, most of the signals that you have seen in the EEG is between 0 to 50, right? So ideally speaking, 2 times that would be your requirements need to satisfy your Nyquist criteria. Each devices has different sampling rate, so they normally hard code it. So that's the limitation that you might feel as a researcher, depends on the applications. But there are other solutions with higher sampling rate also, 1 kilohertz, more than that. So depending on the problem that you are working on it, you can go with these parameters to identify what could be the system to adopt or use it for the research. So as you have seen in the offline data analysis, the feature extraction or the features, list of features was exhaustive, and also the classifiers. So this is one case. I'll also show another case what we did. So you can see here we have a data of around 20 peoples, 20 subjects with two. One is a smiling data and another one is a angry. So we had a protocol to make them happy and to make them angry. So we worked with 20 because we had a limitation on the data. Let me run this case. So we have two phases. In the training phase, you can load all the data of one task and then another one. So one is smile. So we are able to load 20 subjects data. You can load 20 subjects data of anger. So go with the feature extraction. So we went with DWT coefficients here also. So extraction is done. So you can move on to the testing phase. So in the testing phase, we tried out with two classifiers. So you can select any random data set. So we have taken the random data from here. So let me pick up a smile 2. So give a classifier. So it should classify that the person is smiling. The person is in anger. You can also see the accuracy with SVM classifier, maybe 75-80, which can always be 87.5 with these 20 subjects. So you can always increase that. So with K-N classifier, we wanted to compare it. I made a statement that we found out SVM as the best classifier for this set of data. So let me go with K-N classifier. You see the efficiency, right? So you can load different data. So SVM was fine. So we had only two features in this. You can always increase that number of features, and then the training process, and then the testing process. 3 minutes. Yeah. Okay. So we use the videos, right? The standard videos are available for both the cases. One is smiling and angry, right? So we use those videos to stimulate them. So it was fun. They were all final year students, just going for the exam. So we picked up that scenario and then try to acquire the data, right? So we used it's our own protocol, and it's published. So I'll share the paper also, so where we have mentioned about the protocol, right? So the limitations were, the number of subjects were only 20. You can always increase it. The number of features also you can increase it, and then whatever SVM which has been trained here will be able to give you very good efficiency in terms of learning. Yeah, it's from 8 channel, and it's from the same device. It's 8 channel data. It's fine. Any questions? So we touched both offline, how do we analyze it, and then the online. So as a researchers, you can take it forward, because we have our own limitation as a commercial organization. So we are not purely into research, because we wanted to show something to prove the the capabilities. Our objective is totally different than your objective. So you can perceive it from here, and we intend to do that also. So we wanted to enable, we wanted to reduce your time by showing what all we have done it, and from where you can move on, right? I am here. We can also take the offline questions also. Yeah, right. Thank you very much.